Hello everyone. Hope you are doing very well. So, as you all know that today we are going to cover the theory part 3 of the chapter Haloalkanes and Haloarenes. So, let's begin our today's topic. NCRT chapter 6 Haloalkanes and Haloarenes theory part 3, and the section we are going to cover today is section 6.3. This is disclaimer. The objective of today's lecture. So, after attending this lecture, you will be able to correlate the structures of haloalkanes and haloarenes with various types of reaction. So, today we are going to learn about the correlation of the structures between the haloalkanes and the haloarenes with the help of various reactions. The topics that we are going to cover today according to the NCRT. First of all, the section 6.3, that is the nature of XBond, that means carbon halogen bond. Then we will practice an example 6.2, and then we will also see or solve an Intext question 6.1. So let's begin with our first topic 6.3, nature of carbon halogen bond. So the polarity. So basically, we are going to talk about the nature of the carbon halogen bond. That means the bond that is formed between the carbon and the halogen atom in any haloalkanes or haloarenes. Okay. First factor is, or first thing is polarity. The halogen atom, which we are using here for its representation X, the halogen atom X is more electronegative than the carbon, which results in the bond polarity. So halogens are known for their electronegativity, right? So electronegativity means they are able, or they have this ability to pull the bonded electrons towards themselves more strongly. Okay, so halogen atom is more electronegative if you compare with the carbon, and this is going to result to give the bond polarity. So this bond forming between the carbon and the halogen is polar bond. The carbon halogen bond is a polar covalent bond. As I said, due to the difference in the electronegativity, and because the halogen atom is more electronegative than the carbon, it is going to result in the polarity of the bond. So bond will be polar covalent bond between the carbon and the halogen atom. Carbon atom bears a partial positive charge here, which we are calling as delta positive, and the halogen atom bears a partial negative charge, which is we are calling as negative or delta negative. Okay, so as I said, that polarity, due to the polarity, which is actually the separation of charges or electrical charges in a molecule or atoms, creating a positive and a negative end, which we are calling here delta positive and delta negative. Okay, so electronegativity is one of the factor, which is the ability to of atom to attract the electrons towards itself. So electronegativity is a major factor which determines the bond polarity, and due to which this carbon halogen bond becomes polar, and as a result the carbon atom will get a partial positive charge, which we are calling as delta positive, and halogen atom gets a partial negative charge, that is delta negative. You can see in this figure, the carbon halogen bond is present. Carbon is having a delta positive charge and the halogen is having a delta negative charge, and this partial positive or negative charge is creating among the carbon and the halogen respectively due to the presence of polar covalent bond between the carbon and halogen. Why? Due to the electronegativity difference between the carbon and halogen, because halogen comparatively is more electronegative, have more ability to attract the electron pair toward itself than the carbon. If you talk about the bond length, so bond length means the bond which is forming between the carbon and halogen, its length. Okay, and if you move down the group, the carbon halogen bond length increases with the increase in the size of halogen. If you go down the group in the group of halogens, the carbon halogen bond length will increase because the halogen size is increasing if you are moving down the group, right? This you all know that in the periodic table in any group, if you move from top to bottom, the which each successive member in the group, the size of the atoms are increasing. So if you talk about the halogen groups, if you go down the group, the halogen size is increasing, due to which the bond that is forming between the carbon and halogen is also, the bond length is also increasing for that. Here is given a table 6.2, A part, where we are showing the carbon halogen bond lengths. So let's say if the bond is between the fluorine and the carbon in the compound CH3F, the bond length corresponding to this bond in the picometers is 139 picometer. Similarly, when chlorine is forming the bond with the carbon in this compound CH3Cl, chloromethyl, the bond length in picometers is 178 picometers. And if you move more down the group, like from fluorine to chlorine to bromine, in the bromomethyl, we are having the bond length 193 picometer between the carbon and the halogen, and the, or you can say bromine. Similarly, in the case of CH3I, the iodine and carbon bond length is 214. Iodine is present at the very bottom of the group, halogen group, right? So this fact is like proving through this table that when you move down the group, the carbon halogen bond length is increasing. You can see this is increasing, 139 to 214, right? Now let's see the another nature of the carbon halogen bond, which is determined by bond enthalpy and the strength. So bond enthalpy means the energy that you are going to require to break that bond. Enthalpy means energy, okay? So with the increase in carbon halogen bond length, the bond enthalpy, which is energy that is required to break the bond between the two atoms, decreases. What we are saying, as the bond length increase, the bond enthalpy decrease. That means the energy that you are requiring to break the bond is decreasing. You are requiring less and less energy to break the bond if the bond length is increasing. Okay, what does it mean? That down the group when you go, the bond length increase, right, due to the increase in the size of halogens in the halogen group. So carbon halogen bond length increase, that means the bond length increase means the distance between the carbon and the halogen atom increases, due to which their gap increases, and due to which you can easily break the bond and remove the halogens from the carbon, right? So that's why we are saying that when the bond length is increasing in the carbon halogen bond, the bond enthalpy or the energy that you are providing to that bond to break it is decreasing. You will need lesser amount of energy to break that bond. So bonds becomes weak. What does it mean? You are requiring lesser energy to break the bond, means bond is becoming weak. So this is table 6.2b part, which is showing the carbon halogen bond length, bond enthalpies. Okay, so we have given again for the similar compounds like fluoromethyl. For fluoromethyl, the carbon halogen bond enthalpies in the kilojoule per mole unit is 452. Similarly, for the chloromethyl, we have the bond enthalpy as 351. For bromomethyl, we have 293 kilojoule per mole as bond enthalpy of carbon bromine bond. And in the iodomethyl, that is for the bond between iodine and carbon, the carbon iodine bond enthalpy is 234 kilojoule per mole. So as you are moving down the group in the halogen, the bond enthalpy of carbon halogen bond is decreasing due to the increase in the bond length, right? Next, we will talk about the dipole moment of carbon halogen bond. Okay, so dipole moment means dipole moment is basically a measure of separation of positive and negative electrical charge in a molecule. Okay, So due to the electronegativity, or due to the polarity, okay, there is a partial positive and partial negative charge on the carbon and the halogen respectively, right? And due to these separation, okay, the measurement of this separation of positive and negative electrical charge in a molecule is referring to as dipole moment, and it is a vector quantity. That means it is having both magnitude and direction. So with the increase in the bond length, the dipole moment will also increase. So if the halogen carbon bond length is increasing, the dipole moment of that bond will also increase. Okay, because greater distance, with the increase in the bond length, there will be greater distance between the charges, right? Greater distance between the charges means charge is present on our atoms, like partial positive on carbon, partial negative on halogen, right? So with the due to the polarity, there is this distribution of partial negative partial charges on the both atoms between the carbon halogen, right? And due to this, the bond length is increasing, and bond length is increasing means the separation between these two atoms, or you can say these two positive negative charges, is increasing. And if the separation is increasing, the dipole moment will also increase. So greater distance between the charge means greater dipole moment, because if you know the dipole moment formula, it will be charge into distance, right? So charge are separating more and more, that means distance will increase, that means dipole moment will increase. With increase in electronegativity, the dipole moment increases. Similarly, if you take the factor of electronegativity means the ability of an atom to attract the bonded electrons towards itself more strongly. So if for any atom, the electronegativity increase, so for this bond between carbon and halogen, if the electronegativity is increasing for the halogens, the dipole moment of that bond will also increase, that it is forming with the carbon. Okay, why it is so? High electronegativity means that electron will pull closer to the towards the more electronegative atom in a bond, right? Which creates a greater charge separation, and charge will be larger, that means dipole moment will be greater, because according to the formula Q times D, Q is higher, charge is higher, so dipole moment will increase. Okay, so electronegativity is ability of pulling the electron closer towards itself, and when the electron pulls closer to towards the more electronegative atom, it will create a greater charge separation, due to which the dipole moment increase for this carbon halogen bond. This is a table 6.2 part C. Now this is showing the carbon halogen dipole moments value. So similarly, the same molecules showing the carbon halogen bond and their dipole moment values, corresponding dipole moment values in the dBA unit. So fluoromethyl, okay, that means CH3F, the bond is between carbon and fluorine. So the dipole moment for this bond is 1.847 dB. Similarly, for chloromethyl, we have dipole moment value as 1.86 dB. For bromomethyl, we have 1.83 dB dipole moment, and similarly for iodomethyl, we have 1.636 dipole moment, that is 1.636 dB dipole moment, right? And these are the factors that you have to remind, that if you see that down the group bond length is increasing, so dipole moment will also increase, and if there is electronegativity increase, the dipole moment will also increase. Okay, so there is a note on dipole moment. What is it? Dipole moment of CH3Cl is slightly higher than CH3F. That means dipole moment of chloromethyl is slightly higher than the fluoromethyl. And why is it so? So dipole moment of why the chloromethyl is higher or slightly higher than fluoromethyl. So this is the exception case. Why? Due to the combination of bond length and the charge separation factor. Because that is what the dipole moment formula is. Mu equals to Q times D. Q is the representation for charge and D is the representation of distance between the atoms forming the bond, right? So due to these two factors, that is bond length and the charge separation, and the combination of these two factors will cause the slightly higher chloromethyl dipole moment than the fluoromethyl. Okay, so fluorine is our more electronegative halogen atom because it is having larger charge. Then the carbon and chlorine bond is significantly longer because it is having larger d. Okay, so both the factors are like contributing. Fluorine is more electronegative than chlorine, so larger q it is having, larger charge it is having. CCl bond, that is carbon chlorine bond, is significantly longer, so bond length is increasing. That means it is having larger separation, larger distance. So the product is maximal for CH3Cl. But here what happens, that the bond length in the carbon chlorine bond is larger than the carbon fluorine bond, which compensate for slightly smaller charge separation in the carbon chlorine, and that's why the chloromethyl will be having more dipole moment than the fluoromethyl. Okay, so both the factors are we are considering, but here the fact that the carbon chlorine bond length is greater than the carbon fluorine bond, and this fact is compensating the slight smaller charge separation of carbon chlorine bond, and hence the dipole moment of chloromethyl will be slightly higher than fluoromethyl. This is important. This is an exception case. Okay, so let's solve an example. Example 6.2. The example is, write the IUPAC names of the following. So we have given different structures of 6 molecules. We have to write the IUPAC name of these, right? The first structure is given as CH3CH double bond CH single bond CH BR CH3. Similarly, the second structure where CH2 double bond CH3 single bond CH BR CH3. Third is CCH3H double bond CCH3 single bond CHBr CH3. Fourth is CCH3H double bond CCH3 single bond CHBrH. Fifth, CCH3H double bond CH single bond CHBrH. And sixth is CH2 double bond CH3 single bond CHBrH, right? H is a representation for hydrogen, Br is for bromine, CH3 is for methyl group, and C is for carbon. Okay, so they are unsaturated hydrocarbon structures. You have to tell the IUPAC name of these all. You have given some time. Try to solve this and then we will see the correct answer. Okay, let's see. So, let's start with our first structure. This is the structure given for the first molecule. Okay, so as per the IUPAC nomenclature, first of all, we have to select our longest parent chain and then we have to number the carbon atoms present in that parent chain, right? And the halogen containing carbon should get a lowest possible number if it is an saturated hydrocarbon, but if it is unsaturated hydrocarbon, then double bond will get the lowest number. Okay, so according to these rules, we have to select first of all the longest possible chain in which maximum number of carbon will be there. So if you see carbon this double bond carbon, this double bond carbon, then this single bond carbon, and then this carbon. If you contain this in a single chain, or if you take this chain as your parent chain, this will be the only chain present in this structure that can be parent chain, that can hold the maximum number of carbon present in this structure, right? Now the second thing is numbering. So numbering should be done. If it is unsaturated, then double bond should get the lowest possible number. So because it is the first carbon, so you will number this carbon as first, so that the double bond carbon will get the smallest number. So C1, then here 2, 3, 4 and 5 on the last carbon in the chain, right? Now when you done the numbering, then you have to name it according to the IUPAC, right? So bromine and the double bond is present, okay, and their numbering is also present. Like bromine is present on 4th carbon, and the double bond is present in the between the 2nd and the 3rd carbon. So we consider in the name the smallest number carbon, that is 2nd carbon. So the IUPAC name of this compound will be 4-bromo. Number of carbon total present in our parent chain is 5, because numbering is done until 5, right? So 1, 2, 3, 4, 5. We can't number the hydrogen. We have to only number the carbons which are present in our parent chain, okay? So this parent chain has, or this compound has the name 4-bromo pent, because we have 5 number of carbons, 2 because at the 2nd position we have double bond ene, okay? Ene is the representation for alkene, and alkene unsaturated hydrocarbons, because double bond is alkenes, okay? So the name of this, or IUPAC name of this compound will be 4-bromo pent 2-ene. Now let's see the second structure. Second structure is this one. The similar process you have to follow, the similar steps you have to follow. First of all, you have to select a parent chain containing maximum number of carbons. So if you see, if you start from this carbon, okay, so this and this 4 carbon will be there. If you start from this carbon, 1, 2, 3, 4 carbon will be there. Again, if you start from this carbon, 1, 2 and at this carbon 3, there will be 3 carbons. So only possible carbon that can be present maximally in the parent chain is 4. 4 carbon can be present as maximum, right? So we have choices from 1, 2, 3, 4 or from 1, 2, 3, 4. Okay. So here you have to put the lowest possible number at the double bonds. So if you take this chain as 1, 2, 3, 4, then double bond will get 2 second position carbon, right? But if you start from this carbon and then you will move at the 2nd carbon, which is also having double bond, then the lowest possible number that is gaining by the double bond atom is 1. So 1 is lower than 2, right? So we will consider this parent chain that is already marked. So now the numbering you have to done, it is simple. Start from first carbon and end at the last carbon. So 1, 2, 3, 4. At the 3rd position carbon, we have bromine as a substituted group, and at the 2nd position we have a methyl group as a substituted group, right? So this you have to remember while naming. So the IUPAC name of this compound will be, first of all, the substitution will come as per like alphabetical order. So bromine, 3-bromine. At the 2nd position we have methyl, so 2-methyl. We have 4 number of carbons in our parent chain, so but. At the 1st position we have double bond, so 1-ene. 3-bromo, 2-methyl, but 1-ene. Ene is representation, or ene is representing double bond. So the IUPAC name of this compound will be 3-bromo, 2-methyl, but 1-ene. Now let's see the third structure. Third structure is this, where the same step you have to follow, selecting the parent chain containing maximum number of carbons. Let's see. So if you start from this carbon, at which 2 is written here, so 1, 2, 3, 4, you will get 4 number of carbons in your parent chain. If you start from this carbon, 1, 2, 3, 4, or 1, 2, 3, 4. Then 4 number of carbon is coming. But if you start from the 1 carbon that is already marked, 1, 2, 3, 4, 5, you got 5 carbons in your parent chain. So it is the maximum carbons that that parent chain can hold in the structure. So this is considered as parent chain. So numbering will be start, in which the lowest possible number will be given to the double bond carbon. So 1, 2, 3, 4, 5. Okay, because if you start from here, like from 5, 1, 2, 3, 4, 5. So it will come the lowest possible number as 3, right? But 3 is greater than 2. So we will consider from first carbon to fifth carbon numbering, like from left to right, not from like here from down left, down right to left up. Okay, so 1, 2, 3, 4, 5. Now the substituted groups is bromine, and at the third position we have methyl. Okay, so the IUPAC name of this compound is 4-bromo. At fourth position we have bromine. 3-methyl. At third position we have methyl. Pent 2-ene. Pent, why? Because 5 number of carbons are present in the parent chain. So 4-bromo, 3-methyl, pent 2-ene. Because second carbon and third carbon both are involving in double bond, but we put the lower number in the name, so 2-ene. Okay, so this is the IUPAC name for this structure. Now, let's move to the fourth structure. The fourth structure is given as this, where again you have to do the parent chain selection. So the carbons will get 2 and 3. Now, if you start doing the numbering from bromine carbon, because bromine is substituting to it. So 1, 2, 3, 4. Now again you are getting 2 and 3 at the double bonded carbon. So this will be more beneficial because bromine is also getting a lower number, right? Bromine carbon is also getting a lower number in this case. So this is preferential numbering of the structure. So you will do 1, 2, 3, 4. At the first position, bromine. At the second position, we have double bond. So the IUPAC name of this compound will be 1-bromo, 2-methyl, but because 4 carbons, and 2-ene because lowest from 3 and 2 is 2. So 1-bromo, 2-methyl, but 2-ene is the IUPAC name of this compound. Now let's see the fifth structure. The fifth structure is this one, where you can see that we are having this structure, and you have to select the parent chain, right? You can think that this structure is kind of similar to the fourth one, but no, it is different. How? Because at this place there was methyl group present in the previous structure, but here it is hydrogen. Okay, the similar rule will be followed because only methyl group changed. So the number of carbon will be maximum will be 4 in the parent chain, and numbering will start from the bromine carbon, because in this way the double bond and the carbon that is attaching to the bromine both will get lower number possible, right? So 1, 2, 3, 4. IUPAC name of this compound is 1-bromo, but 4 number of carbons, 2-ene. At the second position we have ene. So 1-bromo, but 2-ene. Then let's see the last and the sixth structure, which is this one. Here also same steps you have to follow, that select your parent chain. The maximum possible carbon in the parent chain can be 3. 1, 2, 3, 1, 2, 3. Okay, only 3 carbons can be there in the parent chain. Okay, so we are putting the one at the carbon at which the double bond is present. So 1, 2, 3. Okay, because 3 number will be given to the bromine carbon. Now the IUPAC name of this compound will be 3-bromo, because at third carbon we have bromine, and 2-methyl, because at the second position we have methyl as a substituted group. 2-bromo, 3-bromo, 2-methyl, propene. Okay, because from the first carbon, the double bond starting, so we are just writing propene. Or you can also write it as 3-bromo, 2-methyl, prop 1-ene to justify the or to show the position of double bond at which carbon it is there. It is at 1. You can simply write it as propene. It will be understood that double bond is present at first carbon. And if you want to write particularly, then you can write it as 3-bromo, 2-methyl, prop 1-ene to represent the position of the double bond. Okay, so you can write in the both way, both are correct. Okay, now let's see this Intext question. Let's solve this Intext question 6.1. Question is, write the structures of the following compounds. The compounds are given as first, second, third, fourth and fifth. That is 2-chloro, 3-methylbentane, 1-chloro, 4-ethyl cyclohexane, 4-tertiary butyl 3-iodoheptane, 1,4-diabromo-but-2-ene, or 1-bromo 4-secondary butyl 2-methylbenzene. So these are the names. You have to convert it into the structure. Like you have to write the structure of these compounds. You have given some time. Try to analyze this question and then we will see the correct answer, the correct structures. Okay, let's see. So let's see let's see the stepwise. The step 1 includes, while writing the structure of the compounds, step 1 includes the identification of parent chain or the ring, parent ring, which is going to give you the root name of the structure or the root name of the the compound that is given. Usually it is the last part of the name. It is written at the last part. Okay, so we have already given the names, so you can identify that what is root name in each of the compounds. The examples are hexane. Hexane means 6 carbons. Cyclohexane. Cyclohexane means 6-membered ring. Benzene. Benzene means benzene ring, and they are the root names. That means they are present at the last part of the name, and they are actually parent chain name or ring, parent ring name. Step 2. What is this step 2? Identify the functional groups, either present or not. Suffix and prefix. They will decide suffix and prefix in the name. So determine the primary functional group first of all. Okay. And then indicated them by the main suffix. For example, ol for alcohol, on for ketone, oic acid for carboxylic acid. These are the functional groups that you will study further. So the primary functional group will be indicated by main suffix. For example, in the hexanol, the OL as a suffix present here is indicating that an alcohol functional group is present in the structure. Step 3. While determining the structure, step 3 is identify and place the substituent, that is the prefixes. So they are listed as prefixes at the beginning of the name. Okay. So identify the all alkyls, halogen or other non-functional group substituents that is present at the very beginning of the name. For example, alkyl groups like methyl, ethyl, halogens like chloro and bromo, or other non-functional group substituents that are present at the very beginning of the name as prefixes that you have to identify and place them as substituents in the structure. There is a note that their positions or locants and quantities, that is dia, tri or tetra. Note the positions and the quantities of these side groups or substituents, okay, that you are going to place as substituents in your structure, which are present as prefixes in the very beginning of the name. Okay, so you have to note their positions if there is given using the numerical thing like 1, 4, 1, 2, ortho, secondary, tertiary, okay, and their quantity, diachloro, diabromo, okay, so dia, tri, tetra. For example, in the 2,3-dimethyl butane, what you can identify that there is dimethyl, that means two methyl groups are present in the structure. There is one on the carbon 2 and one on the carbon 3. There is a presence of two methyl groups. Okay, one is present at the second carbon in the structure and one is present at the third carbon in the structure. That is according to the parent chain. Okay, parent chain numbering. So at second position we have methyl, at third position we have methyl. That's why we are writing a 2, 3, which is the positions of the substituents methyl, and dia means its quantity, that they are 2. Attach these substituents to the parent chain or ring at their specified position. Now what you have to do when you identify these substituents and their positions or their quantities, you have to attach these substituents to the parent chain or the parent ring at their specified positions. So let's now see one by one the diagrams, the structures. First is 2-chloro-3-methyl pentane. So you can see that there is at the second position chloro, at the third position methyl group, and we have 5-membered pentane, that means alkane chain, parent chain. Okay, so draw the 5-membered 5 carbon here first of all, number them 1, 2, 3, 4, 5 in any way, and put at the second carbon 1 chlorine and 1 methyl at the third carbon, and then fulfill the other valencies that have left for each carbon. Okay, so you will get a structure of 2-chloro-3-methyl pentane in this way. And for the second structure, that is 1-chloro-4-ethyl cyclohexane. First of all, cyclohexane means there is a cyclic ring of hexane. Okay, there is cyclic hexane ring, that means 6-membered ring. And at the first carbon we have chlorine, at the fourth carbon we have ethyl as a substituent. So we draw first of all a cyclic 6-carbon hexane ring. Then at the first position you put chlorine and whatever you have considered the first carbon, relative to that at the fourth carbon, like if you consider this as first, so second, third, fourth, this will be the fourth. So at the fourth carbon put the ethyl substituents C2H5 and you get your structure of 1-chloro-4-ethyl cyclohexane. Now for the third compound, that is 4-tertiary butyl 3-iodoheptane. First of all, we have at the fourth position, we have tertiary butyl group present. At the third position, we have iodo substituent present. Heptane means we have a single alkane chain having no substituents other than 7 carbon present in the line or in the chain. Okay, so you can write it as, like, you first of all have to put 7 carbons in a chain. Okay, then at the third carbon you have to put an iodine as a substituent, and at the fourth carbon you have to put a butyl or tertiary butyl group. Tertiary butyl means that that is a butyl and it is containing 4 carbon and it is a tertiary like substituent. How? The carbon that is going to attach at the fourth position carbon, this carbon is also attaching with 3 other carbons of methyl, right, forming a tertiary butyl substituent, and we are attaching it as fourth position. After that, fulfill every other valency for the every and each carbon, and then you will get a structure of 4-tertiary butyl 3-iodoheptene. For the fourth compound, 1,4-diabromo-but-2-ene. So at the first and the fourth position you have bromines. So we have 2 bromines in the structure at the first position and the fourth carbon. And we have but means 4 carbon present in the parent chain. At the second position we have double bond, ene is given, right? So you first of all have to put 4 carbons in a chain. At the second positions you have to mark double bond between second and third, right? Then double bond should be between second and third. That's why you're writing 2 here in this name, right? Because if the bond is between 1 and 2, that is also a possibility. So name should be in the name there should be 1 at the place of 2, right? But it is 2, so we are placing double bond here between 2 and 3. Now at first position put a bromine, and fourth position put a bromine. So we have put it 2 bromines in this structure. We have 4 carbons. We have second position at double bond at second position. Other than that, like complete the structure by filling every valency by the hydrogen with the hydrogen, right? And you get the structure of 1,4-diabromo but 2-ene. Okay, lastly we are left with this fifth compound, that is 1-bromo 4 secondary butyl 2-methyl benzene. So here at the first position we have bromine in the structure. At the fourth position we have secondary butyl structure. At the second position we have methyl as a substituent, and we have a parent ring as benzene ring. Okay, so you first of all have to draw a benzene ring. Consider a first position at which you have to place the bromine. So let's say you are considering this carbon as a first carbon, so you will attach it with bromine. Relative to this first carbon, at the second carbon put a methyl substituent, and at the fourth position relative to the first carbon you have to put a secondary butyl. That means 4 carbon chain, and the carbon that is going to attach with the fourth carbon in the benzene is going to be a secondary carbon, because that carbon is going to also attach with another 2 carbons. Okay, that's why we are writing as secondary butyl for justification of this bond which is forming with which carbon of this butyl and between the fourth carbon of benzene. Okay, and after that you will justify, or you will fulfill all the valencies of the carbons with the hydrogens, the remaining valencies. Okay, carbon is a tetravalent atom, so you have to fulfill 4 valencies with different atoms or hydrogens, and then you will get the structure of 1-bromo 4 secondary butyl 2-methyl benzene. Okay. Okay, let's see the summary what we have done today. Carbon halogen bond, that is CX bond, is polar covalent bond. Why? Due to the electronegativity difference which is present between carbon and halogen, because halogen is more electronegative compared to carbon. And with the increase of size of halogen atom in the carbon halogen bond, the bond length is increasing. This will increase the bond enthalpy also. Okay, this will decrease the bond enthalpy also. Okay, because bond length is increasing, so it is easier to remove the halogen from the carbon halogen bond. So bond enthalpy, that is the energy that you are required to break that bond, will decrease. Down the group, if you go in the halogen groups, the dipole moment for the carbon halogen bond increases due to the increase in the bond length. Dipole moment of CH3Cl, that is chloromethyl, is higher than fluoromethyl, right? So dipole moment of chloromethyl is higher than the fluoromethyl. This have this specific reason that in the carbon bond, in the chlorine carbon bond, the distance, or basically the bond length, is more than the fluorine carbon bond, and this will compensate the slightly lower or smaller charge separation in the chlorine carbon bond, and due to which there is a slightly higher bond dipole moment of chloromethyl than in the fluoromethyl. So this is the table through which we have seen the different bond length values in picometers, the carbon halogen bond enthalpies in kilojoule per mole, and the dipole moment values in the dBA units for fluoromethyl, chloromethyl, bromomethyl, and iodomethyl down the group. Okay, so 139, 178, 193, and 214 in the picometers are the bond length down the group. 452, 351, 293 and 234 in kilojoules per mole are the bond enthalpies of carbon halogen bond present in these halogen compounds. And the dipole moment values in dBA 1.847, 1.86, 1.83 and 1.636. Okay, so this is the major topics or major concept that we have covered in today's lecture. Okay, thank you so much. That's all for today's chemistry session. Thank you.